All right. Hello and welcome, fellow math enthusiasts. This video is about um, how three noncollinear points determine a circle. So, with 2 points determine a line. 2 points for a circle isn't enough. If you had 2 points, then you can draw, conceivably many circles through those 2 points. But three is enough to kind of pin it down and actually have just one unique circle that goes through the 3 points. And this gets into some linear algebra, which is pretty neat. And it actually connects it back to the idea of a slope of a line, which is pretty neat. So first, to show that there's a unique line that contains these three non-collinear points, you start with your 3 points. So just pick x1, y1, x2, y2, x3, y3. So you have 3 points in the plane. And they're non-collinear, so they don't all lie in a single line. They form a triangle, is how you can kind of think of it. So what that means is that if you were to take the slopes of, if you have 3 points here, right? If you look at their slopes, the slopes of any two pairs are going to be different. That's one way to think of it. And that's, in fact, how we connect it back to a determinant, which is what we'll see down here. Okay. So if one of the edges happen to be vertical like this, then you can kind of change the argument a little bit down here. If you're looking at the slopes, you just wouldn't choose the slope of that line. You would choose the other two. Or by changing coordinates, just by kind of rotating the axes, you could probably do that too to make it work. But anyways, you start with the three noncollinear points. The equation of a circle is given here. I think this is usually called the general form of a circle. The standard form is with the center and the radius. So I'm working with the general form here. So if the 3 points are on this circle for some parameters d, e, and f, then we get a system of equations for those 3 parameters, d, e, and f. Okay. So we're given the points, and if they all lie on the same circle, then they all satisfy the same equation. So we set that up, and what we get is a linear system in d, e, and f. And what we do is we change this into a matrix system, which makes it easier to look at. If you know about systems of equations and matrices, then that's a nice way to look at it. So first you can get these x1 squared, y1 squared, x2 squared, y2 squared, and so on. You can get those over to the other side. That's this here. And then the coefficients, the coefficient matrix is x1, y1, 1, okay? x2, y2, 1, x3, y3, 1. So that's the coefficient matrix, and you got d, and f right there. So if we can solve this, we can find a d, and f that works, then we get our unique solution, our unique circle that passes through those points. So we know that there's a unique solution here if and only if the determinant is non-zero, or in other words, that the matrix is non-singular. That's another way to say it. So we just have to look at the determinant. So if you calculate the determinant of this matrix here, I expanded by minors with the top row, so x1 times this minor, okay, minus y1 times this minor, x2, x1, x3, x1, and then the last minor, x2, y2, x3, y3. So you multiply that out, okay, expand it out. So compute those determinants here. And then, so in the next line here, and this would depend on, I think, which slope is non-zero. but assuming that you could pick any one, I use x1, y1. So I added and subtracted the same value on the same side. And what that allows you to do is kind of regroup. So then you can regroup down here and then factor it even further. Okay, so what I did was I added these on. So expand this all out. So you just have these products down here. And I grouped them together in a couple different pairs. So I grouped these four, I think, this one and this one. So I grouped those two together to get this. Then I group that and that. Okay, factor out y minus y1, x1 minus x3. And then this one here was what's left over, the ones that aren't underlined. What did we have? y2, y2. So these two, factor out y2, we get this, x1 minus x3, and then these two, factor out x minus x2, y1 minus y3. Okay, so we have those, group them together so we can factor out, and then we notice these two actually have y1 minus y3. So we can factor out that from those two. So y1 minus y3, x1 minus x2, we get that. And we can do the same thing for the middle two, x1 minus x3, factor that out, and we get y2 minus y1. Okay, so up to here, we just evaluated this determinant. We did this little algebra trick, okay, at the bottom here, and then we end up with this. So what to notice at the end here is that this is equivalent to, again, as long as the slopes are non-zero, or you're not dividing by zero, I guess is the thing to say, that this is equivalent to saying that the slope through x1, y1, x3, y3, so the slope through that line is not the same thing as the slope through x1, y1, x2, y2. So in other words, using the fact that those 3 points are non-collinear, okay, that's the connection down here at the end. Okay, so if you know that they're non-collinear, then this is true, and then you can kind of work your way back and say that the determinant's non-zero, and then therefore this must determine a unique circle that passes through the 3 points. Okay, so that's kind of the connection between, what was really neat is the connection between the determinant and the slopes of the lines, which is really, really kind of neat. So to say that this determinant is non-zero is equivalent to saying something about the two slopes, okay, two slopes. And it depends on, like I said, if one of the pairs of lines ended up having an undefined slope, then you wouldn't factor with that, and you would have to possibly adjust the numbers that you're adding to both sides. So it just depends on what you have. But anyways, that's a little bit about that. So anyways, I hope you enjoyed it. You can check it out. Other videos. I love math, so this is my thing. So I'll be posting more about this stuff for sure. If you have any suggestions or anything you'd like to see, maybe some exercises or problems done out. So that's a little bit about that. All right. Well, thank you all for watching, and I'll see you soon.